When the sky caught fire. The last spring of the dinosaurs. To understand the magnitude of what happened 66 million years ago, one must first reconstruct the world as it existed in its final hours. This was the end of the Maastrichtian stage, the closing chapter of the Cretaceous period. The planet was characterized by a biological density and climatic warmth that would seem alien to anyone living today. The continents were drifting toward their current positions, yet they remained separated by widening ocean basins, isolating ecosystems and allowing for distinct evolutionary experiments on every landmass. North America was not the contiguous landmass we recognize today. It was bisected by the Western Interior Seaway, a shallow inland ocean that connected the frigid waters of the Arctic to the tropical currents of the Gulf of Mexico. By the very end of the Cretaceous, this seaway was receding, leaving behind vast, swampy deltas and estuarine environments, such as the landscape preserved in what we now call the Hell Creek Formation. The climate was equable, lacking permanent polar ice caps. Forests of conifers and broadleaf trees extended into the high latitudes, and the gradient of temperature from the equator to the poles was much shallower than it is today. However, this biosphere was not entirely at peace. For hundreds of thousands of years prior to the cataclysm, the Earth had been shuddering under the weight of its own internal heat. In what is now Western India, the Deccan Traps had been erupting on a continental scale. This flood basalt province, one of the largest volcanic features in planetary history, had already released massive quantities of carbon dioxide and sulfur into the atmosphere, causing climatic oscillations that stressed global ecosystems. There is a debate among paleoclimatologists as to whether this volcanism had already initiated a mass extinction, priming the biosphere for collapse through warming and acidification. Yet, the fossil record in the Hell Creek Formation suggests that dinosaur diversity remained relatively stable up until the impact horizon. The system was stressed, certainly, but it was not in terminal decline until the sky fell. Recent analyses of fossilized bone tissue have allowed scientists to pinpoint the specific moment of the catastrophe with a haunting precision. By examining the growth lines in the jaw bones of paddlefish and the pectoral fin spines of sturgeons found at the Tanis site in North Dakota, researchers determined that the northern hemisphere was in the embrace of spring. The bone cells revealed that these fish were in a phase of rapid growth, characteristic of the spring and early summer, but had not yet reached the peak growth density associated with the height of summer. This timing was critical for biological selectivity. In the northern hemisphere, the world was waking up. Animals were emerging from winter dormancy, plants were flowering, and many species were in the midst of reproductive cycles, making them maximally vulnerable to environmental disruption. Conversely, in the southern hemisphere, it was autumn. Species there were preparing for dormancy, winding down their metabolic activity and retreating into burrows or hibernation. This seasonal asymmetry may have conferred a slight survival advantage to the southern fauna, a cruel lottery decided by the tilt of the Earth's axis. The continents themselves were different. The Atlantic Ocean was narrower. South America and Africa had separated, but the gap between them was not yet as wide as it is today. India was still an island continent, racing northward toward its eventual collision with Asia. Antarctica was not yet centered over the South Pole and retained temperate forests along its margins. Australia was just beginning to pull away from Antarctica, opening the Southern Ocean. In this world, the dinosaurs were not a fading dynasty, but a thriving empire. The great herbivores, Triceratops, Edmontosaurus, Ankylosaurus, moved in herds across the lowland plains. The tyrannosaurs, apex predators with bone-crushing jaws, stalked the forests and river valleys. Smaller theropods, feathered and agile, hunted in the undergrowth. Flying reptiles, the pterosaurs, soared above the coastlines, fishing in the shallow seas. And in the oceans, marine reptiles, mosasaurs and plesiosaurs ruled the depths. The skies were filled with birds, though not the birds we know today. Most were toothed, archaic forms, some still clinging to trees with clawed wings. The ancestors of modern birds were present, but they were a minority. Small ground-dwelling creatures scratching in the leaf litter for seeds and insects. The forests themselves were in transition. Flowering plants, the angiosperms, had been diversifying rapidly over the preceding tens of millions of years. They were displacing the older conifers and ferns in many environments, creating more productive ecosystems that supported a greater diversity of insects, which in turn supported a greater diversity of insectivorous mammals and birds. The mammals of this time were mostly small, nocturnal, and unremarkable. They lived in the shadows, scurrying through the underbrush, eating insects, seeds, and whatever scraps the dinosaurs left behind. They were survivors by temperament, pre-adapted to endure hardship. This was the world on the last day, a world of immense biological richness, of ecological complexity built over tens of millions of years. A world where the dominant life forms were supremely adapted to their environments. And it was all about to end. The killer from the outer solar system. The agent of this destruction was not a comet, as was once a popular theory, but a carbonaceous chondrite asteroid. This classification is based on high-precision measurements of ruthenium isotopes found in the boundary clay worldwide. Ruthenium is an element extremely rare in the Earth's crust, but abundant in chondritic meteorites. The isotopic signature of the impactor matches that of C-type asteroids formed in the outer solar system, beyond the orbit of Jupiter. It was a dark, primitive rock, rich in carbon, approximately 10 to 15 kilometers in diameter, a mountain floating in the void. The asteroid approached Earth from the northeast, striking the planet at a steep angle of approximately 45 to 60 degrees relative to the horizon. This trajectory, evidenced by the asymmetry of the subsurface crater structure and the distribution of debris, represented the geological worst-case scenario. A vertical impact of 90 degrees would have buried much of the energy deep in the bedrock. A shallow grazing impact of less than 30 degrees might have skipped off the atmosphere or ejected less material. However, an impact at 45 to 60 degrees is optimal for excavation. It acts like a shovel, digging deep into the crust and lofting the maximum amount of vaporized rock and target sediment into the upper atmosphere. The object was traveling at approximately 20 kilometers per second, roughly 45,000 miles per hour. At this speed, it crossed the thin veil of the atmosphere in under 2 seconds. The air in front of the object could not move out of the way fast enough. It was compressed to a plasma hotter than the surface of the sun before the rock even touched the waters of the Gulf. The asteroid had been traveling through space for billions of years. It was a relic from the formation of the solar system, a piece of the primordial disk of dust and gas that never accreted into a planet. It had orbited the sun in the cold darkness beyond Jupiter, occasionally perturbed by the gravitational influence of the giant planets. At some point, perhaps millions of years before the impact, its orbit was destabilized. It began a long, slow spiral toward the inner solar system. For the dinosaurs below, there was no warning. The asteroid was too small and too dark to be visible to the naked eye until the final minutes. Even if they had possessed the intelligence to understand what was coming, there would have been no time to react. The object crossed the distance from the Moon to the Earth in less than 20 hours. It was moving faster than any natural phenomenon the planet had ever experienced. As it entered the upper atmosphere, it began to glow. The friction with the thin air at the edge of space heated its surface to incandescence. To an observer on the ground, it would have appeared as a brilliant streak of light, brighter than the sun, growing larger and larger until it filled the entire sky. The light would have been blinding, searing the retinas of any creature unfortunate enough to look directly at it. And then, in a fraction of a second, it struck. Impact: 100 teratons in a split second. The impact site, located on the Yucatan platform, was covered by a shallow sea roughly 100 to 500 meters deep. The asteroid punched through this water layer as if it were non-existent, vaporizing it instantly. It then penetrated the sedimentary cover, layers of limestone and gypsum, and slammed into the crystalline basement rock of the continental crust. The kinetic energy released in that fraction of a second is estimated at 100 teratons of TNT. This is roughly 4.5 billion times the energy of the Hiroshima atomic bomb. The energy density was so high that the asteroid and the target rock did not merely shatter, they liquefied and vaporized. A massive plume of plasma, superheated steam, and vaporized rock erupted from the contact point, expanding outward into space at velocities exceeding Earth's escape velocity. The physics of crater formation on this scale involves fluid dynamics rather than brittle rock mechanics. The impact excavated a transient cavity approximately 100 kilometers wide and 30 kilometers deep. This hole was momentarily held open by the outward momentum of the ejecta, but gravity rapidly asserted control. The walls of the transient crater, unable to support the steep slopes, collapsed inward. Simultaneously, the center of the crater, which had been compressed downward, rebounded upward in a massive jet of molten granite, rising higher than the Himalayas before collapsing back on itself. This collapse formed the Peak Ring, a circular mountain range inside the crater. Drilling into this ring in 2016 revealed that the granite had been shocked and fluidized, behaving like a viscous liquid for roughly 10 minutes before freezing in place. The immediate vicinity of the impact was simply erased. There was no transition, no gradual destruction. Everything within several hundred kilometers was instantly vaporized or melted. The rock itself turned to vapor. The water turned to superheated steam. The air turned to plasma. It was not a conventional explosion, but a complete conversion of solid matter into energy and gas. The shockwave radiated outward through the Earth's crust at supersonic speeds. The ground heaved and buckled. Faults that had been dormant for millions of years suddenly ruptured. The entire tectonic plate shuddered under the impact. The shockwave reflected off the boundaries between different rock layers, creating complex interference patterns that amplified the destruction in some areas and lessened it in others. Above the crater, the ejecta plume continued to rise. It punched through the stratosphere, through the mesosphere, and into the edge of space itself. The plume was a mixture of vaporized rock, molten droplets, and solid fragments, all moving at velocities measured in kilometers per second. The larger fragments fell back immediately, creating secondary craters around the primary impact site. The smaller fragments, the molten droplets that would later solidify into glass spherules, continued upward on ballistic trajectories that would carry them halfway around the world. The energy released by the impact was not evenly distributed. The angle of impact meant that more ejecta was thrown to the northwest than to the southeast. This asymmetry would later be visible in the distribution of impact debris across North America. The thickest deposits of spherules and shocked quartz are found in what is now the western United States, while the eastern seaboard received a lighter dusting. The sound that shattered continents. In the immediate aftermath, from the first minute to the first hour, the devastation within a radius of 1,000 to 1,500 kilometers was absolute. An expanding curtain of debris moved outward from the impact site, driven by a supersonic air blast that scoured the surface, flattening forests and destroying any organism above ground. The winds in this zone exceeded 1,000 kilometers per hour. The sound of the impact was an acoustic weapon. Estimates suggest the sound pressure level reached 340 decibels at the source. For context, the threshold for hearing tissue death is around 180 decibels. A sound of 340 decibels is not merely a noise. It is a high-pressure shockwave capable of liquefying internal organs and shattering rock structures hundreds of miles away. The energy transfer into the lithosphere generated earthquakes of magnitude 10 to 11.5. These seismic waves traveled through the Earth's crust at approximately 5 kilometers per second, ringing the planet like a bell and reaching the far side of the world within 30 to 40 minutes. In the immediate vicinity of the Gulf, the ground motion would have been violent enough to throw boulders into the air and trigger massive submarine landslides, which in turn generated secondary tsunamis. A controversial but compelling hypothesis suggests a direct link between this seismic violence and the intensification of the Deccan traps on the opposite side of the globe. Seismic modeling indicates that the energy focused at the antipodal point, roughly the location of India at the time, could have increased the permeability of magma chambers. The hypothesis posits that the shaking essentially uncorked the volcanoes, transitioning them from a high-frequency, low-volume eruptive state to a massive, continuous outpouring of lava that exacerbated the post-impact climate recovery. The forests of Central America and Mexico were the first to die. The trees were not merely knocked down, but stripped of their bark and leaves, reduced to charred stumps by the thermal radiation and the air blast. The soil itself was scoured away in many places, exposing the bedrock beneath. Rivers were choked with debris. Lakes were drained or filled with sediment. The landscape was transformed into a barren wasteland in a matter of minutes. Animals in this zone had no chance of survival. The thermal pulse alone was lethal. The blast wave that followed pulverized anything that had somehow survived the heat. And then came the ejecta, raining down from the sky in a hail of molten rock. The larger fragments, some the size of houses, created secondary craters. The smaller fragments, still glowing hot, ignited anything flammable they touched. For those creatures farther from the impact, death came more slowly, but no less certainly. The shock wave arrived first, a wall of compressed air that shattered eardrums and collapsed lungs. Then came the ground shaking, violent enough to topple the largest trees and open fissures in the earth. And then, as the minutes ticked by, the sky began to change. Tanis, fish-breathing glass. One of the most significant paleontological discoveries of the 21st century, the Tanis site in North Dakota preserves the first hour of the extinction event in unprecedented detail. Located approximately 3,000 kilometers from Chicxulub, on the banks of an ancient river near the Western Interior Seaway, Tanis offers a forensic snapshot of the chaos. A conventional tsunami traveling through the ocean would have taken 10 to 18 hours to reach this coastline. Yet the fossils at Tanis show evidence of violent inundation occurring much earlier. The mechanism responsible was a seiche. The massive seismic waves from the impact arrived in North Dakota roughly 10 to 15 minutes post-impact. These waves shook the semi-enclosed basin of the Western Interior Seaway, creating standing waves that sloshed back and forth with immense violence, with amplitudes estimated between 10 and 100 meters. This sloshing water surged up the river mouth at Tanis, reversing the river's flow. It carried a slurry of marine organisms such as ammonites and marine fish, and mixed them with freshwater inhabitants like sturgeon and paddlefish, as well as terrestrial debris including trees and triceratops remains. The surge buried these organisms in a rapid, turbulent mudflow that locked them in three-dimensional suspension. Crucially, the fossil record at Tanis confirms the timing. As the seiche waves were burying the fish, the sky began to rain glass. These were microtectites, or spherules, molten droplets of Earth's crust ejected by the impact, which had traveled on ballistic trajectories through space and were now re-entering the atmosphere. The spherules are found embedded in the gills of the paddlefish and sturgeon at Tanis. This indicates that the fish were alive, swimming, and gasping for oxygen in the turbid water as the glass rain fell. They inhaled the impact fallout before being buried by the second or third wave of the seiche. The presence of these spherules in the gills locks the time of death to the duration of the ejecta fallout, roughly 15 to 45 minutes after the impact. The scene at Tanis must have been apocalyptic. The river, which had been flowing peacefully toward the sea, suddenly reversed course as a wall of water surged inland. The water was thick with sediment, churned up from the bottom of the seaway. Fish that had been swimming in the river were swept up in the current, along with marine creatures that had been carried in from the sea. Trees were uprooted and tumbled along in the flood. The water rose rapidly, submerging the riverbanks and flooding into the surrounding lowlands. And then the sky began to fall. The spherules, still molten from their passage through the upper atmosphere, streaked down in their millions. They hissed as they hit the water, instantly cooling and solidifying into tiny beads of glass. The fish, struggling to breathe in the turbid water, gulped them in along with the silt and debris. The spherules lodged in their gills, scratching and tearing the delicate tissue. The water surged back and forth, each wave bearing more debris, more bodies, more evidence of the catastrophe. And then, as suddenly as it had begun, the seiche subsided. The water drained away, leaving behind a thick layer of mud studded with fossils. The fish that had been alive minutes before were now buried, their bodies preserved in exquisite detail, their gills still filled with the glass rain from the sky. When the sky caught fire. Following the seismic and ballistic phase, the atmosphere itself turned into a weapon. The ejecta plume had lofted trillions of tons of vaporized rock and microscopic spherules into suborbital space. As this material fell back to Earth, it re-entered the atmosphere at hypersonic speeds of roughly 7 to 8 kilometers per second. This process generated friction and compressive heating on a global scale. It was equivalent to billions of shooting stars entering the atmosphere simultaneously. The collective infrared radiation from this re-entering material heated the upper atmosphere to temperatures of thousands of degrees. To an observer on the ground, the entire dome of the sky would have glowed red to white hot. While the atmosphere is not perfectly transparent to infrared radiation, enough heat reached the surface to cause catastrophic damage. Calculations of the radiative heat flux at the ground indicate a peak of 7 to 10 kilowatts per square meter. For context, a typical sunny day provides about 1 kilowatt per square meter. A flux of 7 kilowatts is comparable to the heat felt inside an oven set to broil, or standing in close proximity to a large structural fire. This thermal pulse lasted for several hours as the Earth rotated beneath the falling cloud of debris. The radiant heat was sufficient to spontaneously ignite biomass. The critical heat flux for the ignition of wood is roughly 12 to 20 kilowatts per square meter, but lower fluxes sustained over time can dry out and ignite fine fuels like dry leaves, pine needles, and hair. The result was a global firestorm. Soot layers found at the boundary worldwide confirm that massive wildfires consumed approximately 70% of the world's forests. These fires were likely ignited simultaneously across the Americas and then spread as the Earth rotated the falling ejecta into view of the rest of the planet. The fires not only destroyed habitat, but also pumped massive amounts of additional soot into the stratosphere, compounding the darkness that would follow. The fires began in the forests of North America. The trees, already stressed by the shaking and the air blast, were tinder dry from months without rain. The thermal pulse from the sky ignited the canopy first. The flames spread rapidly, driven by winds created by the fire itself. Within hours, entire forests were engulfed. The heat was so intense that the very soil ignited, consuming the root systems and the seed bank buried beneath the surface. As the Earth rotated, the infrared pulse swept across the Atlantic and into Europe and Africa. The forests there, which had no warning of what was coming, burst into flame as the sky above them turned to fire. The animals, confused and terrified by the sudden heat and light, fled in all directions. Some sought shelter in rivers and lakes, only to find the water heated to near boiling by the rain of hot spherules. Others retreated into burrows, where the thick layer of soil provided some protection from the radiant heat. The fires continued to spread for days. They consumed the grasslands of the interior continents. They burned through the swamps and marshes. They climbed the slopes of mountains, where the thin air and high winds intensified the flames. The smoke rose into the stratosphere, forming a thick, oily cloud that began to block out the sun. For the survivors of the initial thermal pulse, the fires presented a secondary threat. The air itself became difficult to breathe, choked with smoke and ash. The carbon monoxide produced by the burning of so much organic matter reached toxic concentrations in some areas. Animals that had survived the heat now suffocated in the poisoned air. And still, the fires burned. They would continue to burn for weeks, consuming everything combustible until there was nothing left but charred earth and ash. The mile-high tsunami. While the continents burned, the oceans were convulsing. The impact created a rim wave tsunami, a wall of water formed by the initial displacement of the ocean and the collapse of the water cavity. Simulations suggest the initial wave height at the crater rim was approximately 1.5 kilometers, or nearly a mile high. As this wave propagated outward into the deeper waters of the Gulf of Mexico, it subsided but remained terrifyingly large. By the time it reached the coastlines of what is now Texas and Mexico, the waves were likely 100 to 300 meters high. The tsunami did not stop in the Gulf. It radiated through the gap between North and South America and into the Pacific, as well as across the Atlantic. The power of these waves was such that they scoured the ocean floor even at great depths. In the Gulf of Mexico and the Caribbean, the tsunami ripped up sedimentary layers deposited over millions of years, mixing them into a chaotic breccia. This erosion created geological gaps, or hiatuses, in deep-sea basins thousands of kilometers away from the impact. The coastal regions around the Gulf were utterly destroyed. The tsunami stripped away entire ecosystems, leaving nothing but bare rock. Islands were submerged. River valleys were inundated for hundreds of kilometers inland. The water carried with it a slurry of sediment, rock, and organic debris, which was deposited in thick, chaotic layers as the waves receded. The marine life in the Gulf had no escape. The shallow water species, which lived on the continental shelf, were swept away by the tsunami. The deeper water species were killed by the shockwave transmitted through the water itself. The pressure pulse from the impact was lethal to fish and marine reptiles over a wide area. Their swim bladders ruptured, their internal organs were crushed. Those that survived the initial shock were killed by the tsunami or by the rain of impact debris that continued to fall into the ocean for hours. The tsunami traveled across the Atlantic, diminishing in height as it spread, but still powerful enough to cause destruction when it reached the coastlines of Europe and Africa. The wave climbed the continental shelves, inundating low-lying areas and scouring the seafloor. The force of the water was sufficient to transport boulders and to carve channels in the bedrock. In the Pacific, the tsunami was less severe, but still significant. The wave had to travel farther and encountered more complex bathymetry, which dissipated its energy. Nevertheless, the coastlines of Asia and the Western Americas were struck by waves tens of meters high, causing widespread destruction. The oceans themselves were transformed by the impact. The massive injection of vaporized rock and seawater into the atmosphere altered the chemistry of the ocean surface. The rain of spherules and debris continued for days, creating a layer of sediment that covered the seafloor. The phytoplankton, the microscopic plants that form the base of the marine food web, were killed by the darkness that followed. Without photosynthesis, the entire marine ecosystem began to collapse. The three waves of death. Once the fires burned out and the waters receded, the Earth entered a phase of prolonged atmospheric toxicity. The atmosphere was loaded with three primary agents of climate change: soot, dust, and sulfur. The soot came from the global wildfires. The dust consisted of fine silicate particles from the pulverized asteroid and crust. But the true kill mechanism was likely the sulfur. The Yucatan target rocks were rich in anhydrite, a mineral composed of calcium sulfate. The impact vaporized this rock, injecting an estimated 67 to 300 gigatons of sulfur into the stratosphere. The combination of dust, soot, and sulfate aerosols increased the optical depth of the atmosphere to the point where sunlight was effectively blocked. For months to years, the Earth was shrouded in a darkness comparable to a moonlit night. This caused the total cessation of photosynthesis. The marine food web collapsed from the bottom up. Phytoplankton died off en masse, causing zooplankton, small fish, ammonites, and marine reptiles to starve in succession. On land, plants withered and died, leaving herbivorous dinosaurs with no sustenance, which in turn doomed the carnivores. While the dust and soot eventually settled, the sulfate aerosols converted into sulfuric acid, which has a long residence time in the stratosphere. These aerosols acted as tiny mirrors, reflecting solar radiation back into space. Global surface temperatures dropped by an average of 26 degrees Celsius, or 47 degrees Fahrenheit. Tropical regions saw temperatures plummet to near freezing, while temperate regions remained frozen for years. This impact winter was the primary driver of extinction for ectothermic animals like the large marine reptiles and non-avian dinosaurs, who could not regulate their body temperatures in the sudden cold. As the sulfate aerosols slowly rained out of the atmosphere, they formed a dilute nitric and sulfuric acid rain. This acidification of the surface oceans was devastating to calcifying organisms. Planktonic foraminifera and coccolithophores, which make shells of calcium carbonate, suffered massive extinctions. The acidity may have been sufficient to dissolve the delicate shells of ammonite larvae, preventing reproduction even if adults survived the initial trauma. The darkness was the first killer. Within days of the impact, the plants began to die. The leaves withered and fell from the trees. The grasses turned brown and collapsed. The ferns, which are more tolerant of low light, persisted for a while longer, but eventually succumbed as well. Without plants, the herbivores began to starve. The great herds of Triceratops and Edmontosaurus, which required enormous quantities of vegetation to sustain their massive bodies, were the first to die. They wandered through the darkened forests, searching for food that no longer existed, growing weaker with each passing day until they finally collapsed. The carnivores followed soon after. The tyrannosaurs, which had feasted on the herbivores for millions of years, now found their prey disappearing. They turned to scavenging, feeding on the carcasses that littered the landscape. But the carcasses eventually rotted away, and there was nothing left. The tyrannosaurs, weakened by hunger, succumbed to the cold and the starvation. The cold was the second killer. As the weeks turned to months, and the stratospheric aerosols continued to block the sun, the temperature continued to drop. The tropical forests, which had never experienced frost, were now subjected to freezing temperatures night after night. The cold killed the remaining plants and animals that had survived the initial darkness. The reptiles, which relied on external heat sources to regulate their body temperature, were particularly vulnerable. They became sluggish and immobile, unable to hunt or escape predators. They froze to death in their burrows or on the open ground. The acid rain was the third killer. As the sulfate aerosols rained out of the stratosphere, they acidified the surface waters of the oceans and lakes. The pH dropped by several units, making the water corrosive to shells and skeletons. The marine invertebrates, which had already been stressed by the darkness and the starvation, now faced a new threat. Their shells began to dissolve. The larvae of many species could not form shells in the acidic water and died before reaching maturity. The world that emerged from the darkness was unrecognizable. The forests were gone, replaced by barren landscapes of ash and charred stumps. The rivers and lakes were choked with sediment and organic debris. The oceans were lifeless, their surfaces covered with a thick scum of dead plankton. The air was still thick with smoke and dust, though the worst of the darkness had passed. Why mammals survived. The shelter hypothesis. The extinction was severe. 75% of species were wiped out, but it was not random. The survivors possessed specific traits that allowed them to endure the thermal pulse, the darkness, and the cold. The shelter hypothesis explains the survival of mammals and certain amphibians. The thermal pulse killed anything exposed on the surface, but soil is an excellent insulator. Animals that lived in burrows, or fossorial species, were shielded from the initial heat. Most Mesozoic mammals were small, shrew-like, and nocturnal, naturally pre-adapted to survive in burrows. Crocodilians, being semi-aquatic, escaped the thermal pulse by retreating underwater. Their slow metabolism and ability to go months without food helped them survive the subsequent famine. With the collapse of living plants, the food web shifted to a detritus-based economy. The only abundant food source was dead organic matter, rotting trees and carcasses. Organisms that fed on detritus, such as worms, snails, and insects, flourished. Small mammals and birds that fed on these insects survived, while the green food web of herbivores eating plants collapsed totally. The brown food web of detritivores eating rot persisted. The survival of birds is a story of a specific filter. Why did birds survive while other dinosaurs died? It appears that only a specific lineage survived, the ancestors of modern birds, the neorniths. Fossil evidence suggests the survivors were ground-dwelling birds with beaks capable of crushing hard seeds. Seeds are durable biological time capsules that can persist in the soil for years. While the forest died, the seed bank remained. Birds that could access this resource survived the impact winter, while tree-dwelling birds that relied on insects or fruit went extinct along with the forest they called home. The mammals that survived were those that could adapt to the new conditions. They were small, which meant they required less food to survive. They were omnivorous or insectivorous, which gave them flexibility in finding food. They were nocturnal, which meant they were already adapted to low-light conditions. And they were burrowers, which protected them from the thermal pulse and the cold. In the months following the impact, these small mammals emerged from their burrows to find a world utterly transformed. The great dinosaurs were gone. The forests were gone. The world was covered in a thick layer of ash and debris. But there was food in the form of dead wood and rotting carcasses. There were insects feeding on the decay. And there were seeds buried in the soil waiting to germinate. The crocodilians survived by retreating to the water. They could hold their breath for hours, waiting out the thermal pulse beneath the surface. Their slow metabolism meant they could survive for months without eating. And when the crisis passed, they emerged to find a world with less competition and abundant carrion. The turtles survived in a similar fashion. They could retreat into their shells and bury themselves in the mud at the bottom of rivers and lakes. The thick shell protected them from the heat and the cold. Their slow metabolism allowed them to wait out the famine. The amphibians that survived were those that could bury themselves in mud or hide in deep water. The frogs and salamanders, with their permeable skin and reliance on moist environments, were vulnerable to the fires and the drought. But those that lived in permanent water bodies, in caves, or in deep burrows survived. The insects, surprisingly, suffered relatively low extinction rates. Their short generation times allowed them to evolve rapidly in response to the changing environment. Their small size meant they could shelter in cracks and crevices, and their larvae, which often lived underground or underwater, were protected from the worst of the catastrophe. A new world of fungi and ferns. The geological signal of the recovery is dramatic. In sediments immediately overlying the impact layer, pollen from flowering plants disappears almost entirely. It is replaced by a massive abundance of fern spores, accounting for 70 to 100% of the flora. Ferns are disaster taxa, pioneer species that can rapidly colonize devastated environments from rhizomes protected underground. This fern spike documents a world where the complex Cretaceous forests had been wiped clean, replaced by a global monoculture of ferns. In some high-resolution records, such as those in New Zealand, an even earlier signal is found: a fungal spike. This layer, rich in fungal spores and hyphae, represents a brief interval where the primary biological activity on Earth was the decomposition of the massive quantity of dead biomass. It was a world of rot, followed by a world of ferns. The recovery took time. For the first 1,000 years after the impact, the Earth was a desolate place. The ferns dominated, but they provided little in the way of food for herbivores. The forests began to return slowly as seeds germinated and seedlings struggled to establish themselves in the damaged soil. The first trees to return were fast-growing pioneer species, adapted to colonize disturbed environments. They were replaced over time by slower-growing but more competitive species. The animals that survived the impact began to diversify. The mammals, freed from competition with the dinosaurs, began to explore new ecological niches. They grew larger. They developed new diets. They adapted to new environments. Within a few 100,000 years, the first large herbivorous mammals appeared, filling the roles that had been occupied by the dinosaurs. The birds also began to radiate. The ground-dwelling seed-eaters gave rise to new lineages that explored different diets and habitats. Some became specialized insectivores, others became carnivores, hunting small mammals and reptiles. Still others returned to the trees as the forests recovered and became arboreal once more. The marine ecosystems took longer to recover. The phytoplankton, the foundation of the oceanic food web, had been nearly wiped out. It took thousands of years for them to recolonize the oceans. As they did, the zooplankton returned, followed by small fish, larger fish, and eventually marine reptiles and mammals. The elimination of the dinosaurs left a vacuum in the ecological niches of large herbivores and carnivores. Within a few 100,000 years, mammals began to radiate rapidly. They grew in size, diversified in diet, and moved from the undergrowth to dominate the planet. The dinosaurs did not fail. The world they were adapted to simply ceased to exist in the span of 24 hours. The evidence, from the microscopic iridium dust to the granite peak ring of Chicxulub, confirms that the extinction was extrinsic and sudden. It was not a slow fade, but a violent interruption that reset the biological clock of the planet. The world that emerged from the darkness was fundamentally different from the world that had existed before. The age of the dinosaurs was over. The age of the mammals had begun. The survivors inherited a damaged but resilient planet, one that would slowly heal over millions of years. The forests would return. The oceans would teem with life once more, and the descendants of the small nocturnal mammals that had cowered in their burrows on that terrible day would eventually evolve into creatures capable of understanding what had happened, capable of piecing together the story from the rocks and the fossils, capable of looking up at the sky and wondering what other dangers might be lurking in the darkness of space. The story of the extinction is a reminder of the fragility of life and the power of chance. The asteroid that struck the Earth 66 million years ago was not aimed at the dinosaurs. It was not a punishment or a judgment. It was simply a rock orbiting the sun that happened to cross paths with the Earth at a particular moment in time. If the timing had been different, if the angle of impact had been different, if the target rocks had been different, the outcome might have been different. The dinosaurs might have survived. The mammals might have remained small and nocturnal, forever living in the shadows of the great reptiles. But that is not what happened. The rock fell, the sky caught fire, and the world was unmade, only to be remade in a new image.